Okay, I'm going to show you very briefly how I would go about measuring a pressure volume curve. And then in the next part of the video, I'll kind of walk you through kind of the theory of what's happening during a pressure volume curve and what parameters you can get from that curve that are meaningful in understanding how a plant would respond to drought. Thinking back to the water potential equation we talked about, there were 4 components in that equation. So the water potential is a function of solute potential or osmotic potential, pressure potential, matrix potential, and gravitational potential. When we're talking about a leaf that's been removed from a tree, we're going to ignore our gravitational potential. We already ignore the matrix potential for cells in a leaf. And so that leaves us with osmotic potential and pressure potential. Now, if you remember, pressure potential is the pressure or the water potential associated with the pressure of the water in a cell out onto the cell wall. And when that water is pushing on the cell wall, there's pressure on the cell wall back onto the contents of the cell. But the pressure of the water or the cytoplasm in the cell out on the cell wall is called turgor or positive turgor pressure, and that's what gives cells structure. When we think about a leaf wilting, that's when it's lost turgor, and so that turgor pressure is no longer positive, it goes to 0. And the water potential when a plant loses turgor is really important in explaining its ability to tolerate drought. So plants that can tolerate drought well tend to lose their turgor at more negative water potentials. And so that's what a pressure volume curve does, is it helps us identify the point when a plant would lose its turgor. And then there's a few other important parameters we can get from that pressure volume curve. Although we're going to be measuring this on a leaf, what we're really measuring is what's happening to the cells inside this leaf. So it's really kind of a cellular measure, a cellular level measurement. It's just integrating all the cells in the leaf. And then you could also do this measurement with stems or roots and get the same kind of information. Okay, so let me show you how we would get the data really quickly, and then we'll stop this and we'll go on to the theory of operation. And then there's an assignment where you actually have to analyze the data for 2 different species and kind of interpret the results from the pressure volume curves. So in order to generate a pressure volume curve, we need 2 variables, and you'll see this better in just a minute. But we're going to take the relative water content of a leaf and the water potential, and we're going to pair those measurements. So we're going to pair the relative water content with a water potential measurement. So we want those 2 things happening at the same time. And then because we're trying to identify the turgor loss point, so the point when there's so little water in the cells that it loses turgor, we need to measure this leaf repeatedly from when it's well hydrated to when it's dehydrated. So we're going to do that by just drying it on a bench. So if I were doing this for real, I would have had this leaf or the cut part of this leaf. So I cut this off a plant just a few minutes ago. I would put this cut end in some water, cover this in like black plastic to allow the leaf to fully hydrate, because we want to start with it in like the healthiest condition we can. So we would fully hydrate it, and then when it's fully hydrated, I would make sure it's all dry on the outside, and then I would go ahead and weigh that leaf. Immediately after I weigh it, I'm going to put it, the lamina in the plastic bag, leaving the petioles sticking out. And I would not seal this up perfectly, but seal it a little bit. And then this would go through the bottom of the chamber head. Then the leaf would go inside the chamber here, and I would measure its water potential. There's 2 reasons for the plastic bag. One is, so we're going to measure this repeatedly, and we want really accurate data to get a good pressure volume curve. When we put it in the chamber to measure water potential, the air from the compressed nitrogen tank coming into the chamber is completely dry. There's really almost no moisture at all in there. That can dry out the leaf while it's in the chamber. especially as this leaf gets drier and drier, our measurements are going to take longer and longer. And so what would happen is that during our measurement, the leaf would actually be getting drier. And so the water potential measurement would no longer match the weight. So by putting it in a plastic bag, it minimizes how much water is lost during the measurement. The other thing it does is after we've made the water potential measurement, we want to dry this leaf out or allow it to dry before we make another pair or another set of measurements. How fast this leaf will dry out really depends on what species it is. So some species I actually have to keep in a bag to slow the water loss down to give me enough time to get everything done in kind of a round of measurements. Some species though, I would take out of the bag and set them on the bench for a little bit to allow them to dry. And some leaves are so resistant to drying that I actually put them on a fan to dry them out faster. So you really kind of have to get a little sense of the species you're measuring before you really get into measuring a pressure volume curve. So let's pretend, I measured the weight and the water potential of that leaf at full hydration. And then I set it on the bench like this for about 5 minutes. And knowing the species, I said, okay, 5 minutes is good. Before I put it in the bag, I'll go ahead and weigh it again, take the weight, then, fairly quickly, as quickly as I can while still being careful, put it back in the bag, put it in the chamber with the chamber head on, and measure a water potential again. I would continue that over and over again. Ideally, I want 15 to 20 measurements. A lot of times that doesn't happen. Sometimes your leaf breaks and you only get a partial curve. There's reasons why you might not get 15 measurements. 15 is probably the minimum. I like to have 15 to 20 to be really confident in the curve, but I've also done curves with more like 8 to 10 measurements if that's all I can get. So that's how you get the data for the pressure volume curves. As I said, in the next section, you'll kind of learn what parameters you can get from the pressure volume curve. And then lastly, you'll have to do that yourselves using some data. The data that you're going to use was collected from a couple species in China. We were looking at the kind of drought tolerance characteristics of a bamboo versus a dicot tree that was growing in the same area. So you'll get to look at that data and make some interpretations. Okay, what we're going to talk about right now is pressure volume curves. Pressure volume curves are a technique we use to quantify the response of plant tissue to water limitation or drought. I'm going to draw the curve that you would kind of expect to get from a pressure volume curve and talk about what's going on in the cells as a plant dehydrates. And so this is a nice technique for quantifying drought tolerance, but also in understanding the response of plants to this measurement, we can kind of understand what's going on in the field if plants are exposed to drought as well. So I just want to go back to our water potential, kind of all the components in water potential. So if you remember, let's say we're going to talk about a leaf, or actually let's talk about a cell for now, because that's really what we're going to focus on in this measurement. So we've got 4 potential components contributing to the water potential of a cell. So the first one is osmotic potential, the second one is pressure potential, matrix potential, and gravitational. And so when we're talking about an individual leaf in the cells in that leaf, we don't really have any gravitational potential. They're all at about the same height. And so we're going to ignore that component. Matrix potential, remember, is that physical potential when water is held in like a pore space. And there's some pore spaces on the wall, cell wall in a cell. And so it exists in the cell, but the bulk of the water is not held in those pore spaces. And so we're going to ignore matrix potential. And the two components we're really going to focus on is pressure potential and osmotic potential. So just as a reminder, this is supposed to be a cell, and here is the water content of that cell. And when that cell is full of water, that water is putting pressure on the cell wall. All right? And so that's where our pressure potential really comes from, is from this pressure of the cell back on the cell wall. Now, at the same time, keep in mind that the cell wall is kind of putting pressure back on the contents of the cell. Again, like a water balloon. If this were a water balloon and the red represents the actual balloon, as you fill it up with water, it's going to get harder and harder to fill up because the cell wall is putting pressure back on the contents as the contents are putting more and more pressure on the cell wall. So we kind of have this contrasting pressures, but essentially pressure potential is going to be positive, if you remember. Oops. So these are going to be positive values because it's the pressure of the water out on the cell wall. At the same time, or in this cell contents, I should say, we have sugar molecules. So the black dots represent sugar molecules. And so the number of sugar molecules relative to the number of water molecules is the osmotic potential. And remember, these values of osmotic potential are going to be negative. So the more sugar molecules relative to water molecules, the more the sugar molecules are going to reduce the potential energy of that water, making it more negative. And the balance of these two variables is going to control what the water potential of the cell is. All right. So now let's go and look at what a pressure volume curve is. Actually, it's going to look like. So what we do to generate a pressure volume curve, we are going to measure the relative water content of a leaf and the water potential of the leaf over and over as the leaf dries. And I'll make a video kind of showing you how you would make this measurement. Once we get that data, though, we plot 1 over the relative water content divided 1 over psi of the leaf. And I'm going to put the water potential of the leaf, but you could do a root, you can do a stem. Those are the three main things that you would do. But what we're really interested in is kind of what the water potential of the cells are doing inside that tissue. And by measuring the whole leaf, we're kind of integrating all of the cells. Relative water content is equals 1 if a tissue is fully hydrated. So 1 minus a fully hydrated leaf would be 0. And so on the left side of this axis, we have a fully hydrated leaf. And on the right side, we have dehydrated. On the y-axis, we have 1 divided by water potential. And so we have negative 1 divided by water potential. And so the more negative the water potential, the more negative it is, the smaller this value gets. So we have more negative values here, and we have less negative values on the upper portion. All right. So this is kind of the axes and what the axes are telling us. And so I'm going to draw a couple different components of this curve. So what we're going to talk about first is kind of starting up here when the leaf is fully hydrated. We're going to measure water potential and relative water content, and then we're going to let it dry, measure it again, let it dry, measure it again. And we're going to keep doing that. And this initial response is going to be nonlinear. It's actually a power function. All right, so it's a nonlinear curve. It looks fairly linear at the top, but you start to see that nonlinearity kind of forming the more and more negative the water potential gets. So
well hydrated here at the top, and it's getting more dry. So let's now look at what's going on in the cell. So let's say, so this is the same cell at two different points on the curve. The first one, we have, let's say, that much water, and the second measurement down here, further down, has a lot less water. The number of sugars doesn't change, but the sugar concentration changes. So in this one, we have higher concentration. Let me change this. So we have higher sugar concentration, or I'm just going to call it solute because it's not always sugars. And that means that the osmotic potential is more negative. I don't know why I put a G. Also, when a plant is fully hydrated, we have all of this pressure of the water out on the cell wall. So we've got lots of arrows. But once it's lost a bunch of water, we have a lot less pressure on the cell walls. And so the pressure potential is also more negative. Now remember, pressure potential are positive values, so more negative just means it's getting closer to zero. All right, so the more water we lose, pressure potential approaches zero. But both variables, notice, are getting more and more negative, and so it makes sense that we're getting further down on the y-axis, or we're getting larger negative values. The reason that this curve is nonlinear is that if you think about a water balloon, when it's really full, that cell wall is really taut, right? It's really tight. It's putting a lot of pressure back on the contents of the cell. And if you let out just a little bit of water, that cell wall is still pretty taut and putting a lot of pressure back on the cell wall. So when a water balloon is fully expanded, small changes in the amount of water don't have a big impact on the pressure the material is putting back on the contents of the cell. However, as you approach the point where the cell wall isn't taut at all, or the water balloon isn't taut at all, the change in pressure is really, really rapid. And so it's a nonlinear response. And so what's happening at the bottom of this curve is that we're approaching zero, or the pressure potential is approaching zero. And so we're getting a lot smaller change in the water potential of the leaf, all right? Because it's not, the cell walls aren't pushing back on the contents very much anymore. And so we're not having a big change, but we're still having a big change in the amount of water that's lost, or that relative water content. All right, so that's why it's a non-linear relationship, and we really see that non-linearity down here kind of at the bottom of this portion that I've drawn here. Okay, so let's see if we can get rid of some of this information. All right, and so let's get rid of our writing over here. Okay, so I've said that this initial portion of the curve, we have a change in water potential as the amount of water is decreased in the cell. We have increasing or more negative osmotic potential along this curve as well, and that's a nonlinear curve. At some point, this curve actually ceases to be nonlinear and becomes very linear. Okay, so we have two kind of portions of this curve. Right when this curve, oops, that's a horrible arrow. Right when this curve becomes nonlinear, that's when water potential equals zero, okay? Because the cell wall's pressure back on the contents of the cell, that's what makes this portion of the curve nonlinear. When there's not enough water to push pressure back onto the cell wall, water potential goes to zero. That is what we call the Turgor loss point. And so we represent that as psi TLP. All right, that's the Turgor loss point. Turgor loss point is when pressure equals zero. Okay? After this point on the curve, we still are losing water, so our relative water content is still declining, and we're still seeing a decrease in water potential, but it's at a much slower rate, right? The change in water potential is much smaller relative to the change in water content. And that's mainly because we no longer have pressure potential affecting our water potential curve, right? So if the water potential of the leaf equals osmotic potential plus pressure potential, we've gotten rid of pressure potential. The only thing left is osmotic potential. Because we no longer have the pressure of the cell wall contributing to the water potential, this relationship becomes very linear, okay? And so what's happening on this portion of the curve is that as we're losing water, the sugar concentration is increasing, and we're getting a more and more negative water potential. The cool thing about this is, since we're doing this over a relatively short period of time, these measurements taken maybe an hour, maybe two, the absolute amount of sugars don't change or don't change very much. And so what we can do is if we extrapolate this linear line back to the intercept, we can infer what the osmotic potential was at full turgor. All right, so that point is the osmotic potential at full turgor. All right, so that tells us the sugar concentration kind of when the cell was full of water. We can also figure out what the osmotic potential is at Turgor loss point. Which isn't used as much. We use this one quite a bit. We use osmotic potential at full turgor, and we use Turgor loss point. Oops, I didn't mean to erase that. And those are the two main things we get from our curve. The other thing, though, that we do get from this curve, which is kind of fun to think about, is the shape of this curve, this initial nonlinear portion. The curvature there is a function of the elasticity of the cell wall. Which we represent as epsilon, which is the modulus of elasticity. And what this tells us is if you have a cell wall that's really elastic, you are not going to see as much curvature in this initial slope of the line, so the blue portion of the line on the pressure volume curve. If you have a really stiff cell wall, we're going to see really strong curvature. So the change in the pressure potential is really drastic for small changes in the amount of water in the cell. All right, so that's all I want to talk about now. I'm going to record a video kind of going through these measurements, and then we'll actually look at some data. And when we look at that data, then we can look at the units on all of these things that we've plotted up. So I hope that helps. I know that's a little bit of a messy figure. Anyway, hopefully it's helpful to you. So the spreadsheet you see here is to analyze a pressure volume curve. And so I'll walk you through this spreadsheet, and then I'm going to give you data for two different species, and you're going to generate pressure volume curves and analyze the data. So I guess let me orient you to what's here on the spreadsheet.
On the far left is some user information you need to enter and adjust to determine the pressure volume curve and the parameters from this curve. This blue box at the top shows your final results from the curve. This table kind of in the middle is includes your raw data and then some values calculated from that raw data. And then you can see a couple figures down here. The one on your right is your pressure volume curve, right? So this kind of looks like that diagram I drew out in the previous part of the video. And then on the left is just the mass of the leaf. Even though it says mass of water, it's mass of the leaf, including the water and the leaf water potential. And you can kind of use this line as a diagnostic feature as well. So on the left, the things you need to enter, you need, sometimes when you're doing this, you will put your leaf in a plastic bag, and that helps slow down the evaporation rate so you can get a curve in a reasonable amount of time. It doesn't happen too fast. So if you do that, you need to enter your bag weight. You need to dry your leaf when you're all done and enter your leaf dry weight. And then you need to enter your leaf area of your leaf in centimeters squared. Then these values down here under the curve parameters, I'm not sure why I entitled that. These are the rows of your raw data. So if this table is your raw data, these represent the rows of different points in the data. And so you're going to adjust these values here in order to identify different portions of your curve. And I'll show you how that works in just a second. Let's talk through the results here real quick. So saturated leaf weight. This is really just how much water there is. Well, it's the weight of your leaf and the water when it's saturated, and that comes from this curve on the left. In this curve, it extrapolates this line up to the y-intercept, so where it equals 0, and gives you the saturated leaf weight. Generally, you want to start this curve with your leaf being saturated, but sometimes it doesn't happen even if you think it does. This is your saturated water content. So this is 17.4% of this leaf was water weight. P sub O is our osmotic potential. So we have slightly different abbreviations than what I used in the video. I apologize. I took this spreadsheet and modified it from somebody else, and I didn't change all this stuff. So this is the osmotic potential at full turgor. Here's your turgor loss point. Both of those are measured in megapascal. Here's your relative water content at turgor loss point. So you can present your relative water content as a fraction. So that means the values would be between 0 and 1, 1 being fully saturated, 0 being completely dry. Or you can multiply that by 100 to do it in percent, whereas 100% would be saturated. These results are presented in percentages. So 94.7% of its total water is when it loses turgor loss point. So that means if it goes from 100% to only 94% water, this plant is dead, or probably not dead necessarily, but it's wilted. All right, so it can't lose very much water before it might be wilted. This E is like the epsilon, so this is the modulus of elasticity in megapascals, and so it's really how much pressure a cell changes relative to a change in water content. CFT is the capacitance of the leaf at full turgor. Capacitance is in units of per megapascal, so it's kind of the inverse of modulus of elasticity, essentially. Well, not essentially. They're correlated, but not exactly the same. And we can talk about that more live if you're interested. So this is the capacitance at full turgor. So how much of a change in the pressure occurs relative to how much water is being lost. This is the capacitance at Turger loss point. And then these two values in O and P are the capacitance at full Turger and Turger loss point normalized by leaf area. The reason these are in here is because they're for another type of measurement we do, we need that data. But for the most part, we won't present it. You wouldn't present this data. And then here's leaf dry matter content. Let's ignore that for now. We can come back to it later in the semester. The things we talked about, though, in the video earlier was the osmotic potential at full Turger, column I, Turger loss point, column J, epsilon, this modulus of elasticity L. Yeah, those are the main things we're going to really look at from these pressure volume curves. Okay, let's see. What else should you know here? Okay, now let's look at the raw data and these three kind of parameters over here. So what you're going to do when you generate data for pressure volume curve is you're going to measure water potential of the leaf and the weight over and over. And that's what you're going to input into columns G and H. The rest of this table will be populated for you. So this is just a -1 divided by the water potential of your leaf. Here's the leaf water, so it's just subtracting the dry weight of the leaf out of your weight. Calculating relative water content as a fraction, relative water content as a percentage. In this case, this is 100 minus relative water content. The way I showed it earlier is 1 minus relative water content. Whether it's 1 minus or 100 minus depends on whether you have relative water content in a fraction or as a percentage. These are parameters I never even use, and so to be honest, I can't remember what they do anymore, so we'll just ignore them. Okay, let's look at, oops, oh well, you can still see me, my light went out, because my slipper fell off, and I was trying to put it back on, and I kicked the light outlet. I'm in the basement, floor's cold, my tootsies get cold. Okay. Let's look at the pressure volume curve here. So this one I've already analyzed. But what it might look like when you start is that it might look something, actually let's make it more extreme. And then you've got data to 28. All right, so the way to start this is you enter the row number of your first row of data, which is often going to be 11. Sometimes it won't. We'll talk about why. Your last row of data, which in this case is 28. And then this row is going to be the row containing the Turger loss point. So the point right before the linear portion of the line starts. And so really there's a couple things you have to look for. First, you want to change this middle point until the R squared over here gets as high as possible. So that R squared is just telling you how well that linear line fits the data. And for us, the closer it gets to 1, the better it's fitting the data. With the caveat, if you get down to 2 points, it's going to be 1. And so you have to, it's a little bit of a judgment call here, because like this pressure volume curve looks really nice and I have lots of data points. There's lots of them that don't look this good, and you have to start using a little bit of judgment call, which is dangerous. But the more you use the pressure volume curves, the more comfortable you get with their ability to actually tell you the right thing. So right now what I'm going to do is, obviously I'm not at the Turger loss point, because the red symbols in this figure, we want those to be all on the linear line. All right, and right now we can see a lot of those are part of the curved line. So these three are definitely on the curved portion. Let's move that down by 3. All right, so if I try the Turger loss point being on row 18 of the data, you can still see there's a lot of curve in these data points, and so I don't have a total linear line. And so I'm going to go up to 20. That's looking pretty good. Some of these down here, this far left one looks like it's a little above the line. It might be in the curved part. And so in R squared, generally you can get it above 0.9, and a lot of times you can get it pretty close to 0.99, and that tells you it's linear. So we're getting closer and closer. That's good. So I'm going to go one more, 21. Yeah, I could potentially be there right now. I'm going to try 22. All right, so now if I look at this after I put it to 22, these red lines are pretty smack dab on the linear line, and this first blue line is a little above it, as if it's still part of that curvilinear part. If it were part of the linear, this line would run right through the middle of that point or that symbol, and it doesn't. So right now I'm starting to feel like I'm getting close. If I go to 23, that line runs pretty close through the middle of that that symbol, and so I would say it's probably somewhere between 22 and 23. And so I'm going to leave it right there as 22. My R squared is 0.89, so it's a bit lower than I typically have, but I'm feeling pretty confident that we've hit that linear portion. And so then all of the blue symbols are in this nonlinear portion of the line. The other things to look for here is there's two things, and I'll try to find a curve that doesn't look as neat as these here in a minute. But the last row, you would think it would always be your last row of data, but what can happen with your data is sometimes, even though you keep losing water, so you get more points off to the right, the water potential can actually start going the other way a little bit. And that's because if there's lots of collapse of the cells and the xylem water could be kind of released from some of the vessels and apoplastic water can get in there, so you can actually get an increase in your water potential at the very end. And so you have to watch for that, and you might remove a couple data points if they look like the line is actually going back up or like flatlining. Remember, it should be this negative slope all the way as sugar concentration is getting higher and higher, and so we should continue a linear line. If it flatlines or start going up, something has happened inside that leaf, and the leaf is kind of toast, and you want to get rid of those data points. The other thing that can happen is that some of your initial data points can be oversaturated, meaning that there's actually the air spaces in the leaf are filled with water when they shouldn't be. So if the plant doesn't normally operate with its air spaces saturated, you shouldn't start your data with they're saturated, right? So what that'll look like is if you look at this figure on the left, these blue symbols are fairly linearly increasing. If these blue symbols start to plateau off, and so we would see these data points kind of like leveling off, that's a sign that you had water in the air spaces, and so your first few measurements were just pushing out that water from the airspace. If that happens, you want the first row of data to actually be, on row 12 or 13. You move it down until you don't see what we call the plateau effect. All right, and that's the only reason you would change where your data starts and where it ends. Other than that, once you kind of have the beginning and the end set, really you're just looking for that trigger loss point, and then the rest of these parameters at the top are going to be calculated from that curve. All right, so that's kind of how you use this spreadsheet. The other video hopefully is fairly clear in walking you through how to interpret or obtain the different parameters from the pressure volume curve. And so I'm going to give you a couple data sets to play with and interpret and think about.